What if the quietest traveler in the universe has been touching your world all day long and you've never noticed it? Every color you've seen today, every shadow on a wall, every soft glow from a lamp or screen arrived carried by something unimaginably small, a particle of light called a photon. These tiny messengers have been crossing the universe since the first stars ignited, moving silently through space, through oceans of darkness, and finally into your eyes. Tonight we're going to slow down and meet them, not in the hurried way of textbooks, but gently, one quiet fact at a time. So settle in, let your breathing soften, and allow the smallest particles of light in the universe to guide you slowly and peacefully towards sleep. A photon is a single particle of light. It is the smallest possible unit of electromagnetic radiation, the tiniest whisper of brightness that the universe can offer. You cannot break a photon in half. You cannot shave a sliver from its edge and hold something smaller. It is already the most delicate thing there is, a fragment so fine that it slips through the spaces between atoms without ever being noticed. And yet, everything you have ever seen, every sunrise, every shimmer on the water, every soft glow of a bedside lamp, was delivered to your eyes by these impossibly small messengers. They are the couriers of the visible world, and they have been arriving at your doorstep since the moment you first opened your eyes. Tonight, they are still arriving, still carrying their quiet cargo of color and warmth, even into the darkness where you now rest. The word photon comes from the Greek word phos, which means light. It is one of the oldest ideas the human tongue has ever tried to shape. This notion that brightness is a thing, a substance, something you could almost reach out and hold. The ancient Greeks looked up at the sun and wondered what it was sending toward them, and they gave that mystery the name phos, which carried within it a kind of reverence, a recognition that light was not simply useful but sacred. Thousands of years later, when scientists needed a name for the smallest piece of that sacredness, they returned to that same ancient root. They reached across the centuries and borrowed a syllable from a civilization that had gazed at the same sky, and they called it a photon. So every time you hear the word, you are hearing an echo of the very first wonder, the very first time a human being looked at the brightness of the world and tried to give it a name. The term photon was first introduced by a physical chemist named Gilbert N. Lewis in the year 1926. But here is a gentle twist in the story. Lewis did not mean by the word what we mean by it today. He imagined the photon as a kind of permanent structural piece of the atom, something that could not be created or destroyed, a fixed and eternal building block woven into the fabric of matter itself. His definition was, as it turned out, incorrect. And yet the word he chose was so beautiful, so clean and musical, that the rest of the scientific world quietly borrowed it and gave it a new meaning. They kept the name and changed the soul behind it. It is a strange and tender thing, the way language works. Sometimes a word outlives the idea it was born to carry and goes on to hold something truer, something its creator never imagined. Lewis gave us the vessel. The universe filled it with light. A photon has zero rest mass. It weighs nothing at all when still, though in truth a photon is never still. This is one of the quiet paradoxes that lives at the heart of light, a riddle wrapped in silence. Mass, for most things in the universe, is what gives them weight, what makes them feel the pull of gravity, what keeps them anchored to the ground beneath them. But a photon carries none of that heaviness. It is unburdened in a way that nothing else in the physical world can claim. It moves through the cosmos without luggage, without friction, without the drag of its own substance slowing it down. And yet it is not nothing. It is not empty. A photon carries energy, carries momentum, carries the power to warm your skin or trigger sight in your eyes. It is perhaps the most beautiful contradiction in all of physics, something that has no weight but is never without consequence, something that is less than a whisper and yet strong enough to cross the universe. Despite having no mass at all, a photon carries both energy and momentum. This is a truth that once puzzled even the greatest minds in science, because in everyday life, momentum belongs to heavy things. A rolling boulder, a crashing wave, a ball thrown across a field. Momentum seems to require substance, something thick and tangible pushing its way through space. But a photon defies that intuition. It pushes without weighing anything. It arrives without mass, and yet it can move things, press against surfaces, nudge the dust of a comet's tail away from the sun. The energy of a photon is bound to its frequency. The faster it vibrates, the more energy it holds. And that energy, though weightless, is real enough to warm the earth, to feed a forest, to power the chemistry of life itself. A photon is proof that strength does not require heaviness, that influence does not require size, that the softest thing in the universe can still shape the world. A photon is classified as a boson, a type of particle whose purpose is to carry force. In the language of physics, there are particles that make up matter and particles that hold matter together, and the photon belongs to the second family. It is a messenger, a bridge, a thread of connection between charged things. Every time two electrons push away from each other, every time a magnet clings to your refrigerator door, every time a compass needle turns toward the north, it is photons that are doing the invisible work beneath the surface. They are the carriers of the electromagnetic force, one of the four fundamental forces that govern everything in the universe. And they do this work in silence, without ever drawing attention to themselves, without ever asking to be noticed. A boson is a servant of the cosmos, and the photon is the quietest servant of all, holding the world together with nothing but light. Photons are the force carriers of the electromagnetic force, which is one of the four fundamental forces of nature. These four forces are the deep grammar of the universe. They are the rules that everything, from the smallest atom to the largest galaxy, must obey. There is gravity, which pulls things together across great distances. There is the strong nuclear force, which binds the hearts of atoms. There is the weak nuclear force, which governs certain kinds of radioactive change. And there is electromagnetism, which is responsible for light, for electricity, for magnetism, for the chemistry that makes life possible. The photon is the ambassador of this electromagnetic realm. Every flash of lightning, every glow of a screen, every signal sent through a wire or beamed from a satellite, all of it is the photon doing its ancient and tireless work. It is remarkable to think that one of the four pillars holding up the architecture of reality is carried on the back of something so small it has no weight at all. A photon exhibits something called wave-particle duality, which means it behaves as both a wave and a particle depending on how it is observed. This is one of the most mysterious truths in all of science, and even the greatest physicists have marveled at it without fully understanding why it should be so. When you send light through a narrow opening, it spreads and ripples like water. It bends around corners, it creates patterns of brightness and shadow that only waves can make. But when you try to detect that same light with a very sensitive instrument, it arrives not as a continuous wash but as individual little impacts, one at a time, like tiny pebbles landing on a shore. The photon is both of these things at once. It is a ripple and a grain. It is a wave that somehow remembers how to be a particle, and a particle that somehow knows how to be a wave. It does not choose between identities. It holds them both, gently, the way a river holds its current and its stillness at the same time. The idea that light comes in tiny, individual packets of energy was first proposed by a physicist named Max Planck in the year 1900. At the time, this was a radical thought. The scientific world believed that energy flowed smoothly and continuously, like water from a faucet, and the notion that it might come in discrete little bundles was deeply unsettling to the established order. Planck himself was uncomfortable with his own discovery. He had been trying to solve a stubborn problem about the way heated objects radiate energy, and the only mathematics that worked required him to assume that energy was not a river but a staircase, not a flow, but a series of tiny, separate steps. He called these steps quanta, from the Latin word for how much. And with that single word, with that one reluctant idea, he opened the door to an entirely new understanding of reality, one that would eventually give birth to quantum mechanics and change the way we see the universe forever. Albert Einstein expanded on Planck's work in 1905, describing light as made of discrete quanta, individual packets of energy that traveled through space as independent units. He did not use the word photon, however. In his writing, he called them Lichtquanten, which is German for light quanta. It was not until 2 decades later, when Gilbert Lewis coined the term photon in 1926, that the scientific community found a word they loved enough to keep. They took Lewis's word and quietly reassigned it to Einstein's idea, borrowing the name from one man and the meaning from another, weaving together two different minds into a single lasting truth. Einstein's paper on the subject was a masterwork of insight. He showed that the way light knocks electrons free from a metal surface could only be explained if light arrived not as a continuous wave but as a stream of individual particles, each one carrying a precise amount of energy determined by its frequency. This explanation would earn him the Nobel Prize, and it remains one of the cornerstones of modern physics. Albert Einstein received the Nobel Prize in Physics in 1921, and it was not for his famous theory of relativity. It was for his explanation of the photoelectric effect, the phenomenon that proved light is made of particles. The photoelectric effect is what happens when light strikes a metal surface and causes electrons to fly free from it. Scientists had noticed that this only worked with certain colors of light, and that making the light brighter did not always help. A dim beam of violet light could knock electrons loose, but even the brightest beam of red light could not. This made no sense if light was simply a wave, because a stronger wave should always deliver more force, but it made perfect sense if light was made of individual photons, each one carrying a fixed amount of energy tied to its color. Violet photons carry more energy than red ones, enough to dislodge an electron. No amount of red photons, no matter how many, could match the individual punch of a single violet photon. It was this elegant, particle-based explanation that convinced the Nobel Committee and forever changed our understanding of light. A single photon is the smallest amount of energy that light can carry at a given frequency. You cannot have half a photon or a quarter of one, or any fraction in between. Light does not come in continuous streams. It comes in whole, individual pieces, each one carrying a very specific quantity of energy that is determined entirely by how quickly it vibrates. A photon of red light carries a certain energy, and a photon of blue light carries more, and a photon of gamma radiation carries more still. But each one is indivisible, complete, whole unto itself. This is the great gift of quantum physics, the understanding that the universe at its very foundation is not smooth but granular, not a river but a rain. Every beam of light that touches your face tonight is made of these tiny, whole pieces arriving one after another, like notes in an endless and exquisitely gentle melody. Each note is perfect. Each note is complete, and together they sing the world into being. In a vacuum, in the pure empty space between stars, a photon travels at approximately 299,792,458 meters every single second. This number is the speed of light, and it is one of the most sacred constants in all of physics. It does not waver. It does not change with the seasons, or the temperature, or the time of day. It is the same in every corner of the universe, the same for every observer, the same whether you are standing still or hurtling through space at unimaginable speed. The speed of light is not just fast, it is the universe's absolute speed limit, the ceiling above which nothing can ever climb. And the photon does not merely approach this limit, it lives there, permanently, effortlessly, as though speed were not something it achieves, but something it simply is. Every photon that has ever existed has traveled at this speed, and every photon that ever will exist will do the same. The speed of light in a vacuum is the fastest speed that anything can travel in the universe, according to Einstein's theory of special relativity. This is not simply an observation about how fast things happen to go. It is a law, a boundary built into the architecture of space and time itself. Nothing with mass can ever reach the speed of light, because the faster a massive object moves, the more energy it takes to push it faster still, and to reach light speed would require an infinite amount of energy. Only massless things can travel at this ultimate velocity, and photons, having no mass at all, are born already moving at this speed. They do not accelerate. They do not build up to it. From the very first instant of their existence, they are already there, already at the edge of what the universe allows. It is as though the cosmos set a single perfect speed for its messengers of light, and every photon has honored that speed since the beginning of time. Photons always travel at the speed of light. They cannot speed up, and they cannot slow down, not in the emptiness of space. This is one of the strangest and most beautiful rules of the universe, that light has only one gear, one pace, one eternal rhythm, and it never deviates. A photon born in the heart of a distant star moves at exactly the same speed as a photon born in the filament of a lamp beside your bed. There is no fast light and no slow light in the vacuum of space. There is only light, moving at the one speed the universe has assigned to it, carrying its energy across the darkness with a constancy that nothing else in nature can match. While everything else in the cosmos accelerates and decelerates, drifts and stalls, the photon simply moves, always, without effort, without variation, as steady as the deepest breath you have ever taken. When a photon enters a medium like glass or water, something subtle and fascinating happens. The photon itself, as an individual particle, always travels at the full speed of light. It does not slow down, but when it enters a material, it begins to interact with the electrons of the atoms it encounters, and these interactions create a kind of combined disturbance, a quasi-particle that physicists call a polariton. This polariton, this mingled dance of light and matter, moves through the material more slowly than light moves through empty space. So the wavefront of light, the overall signal, the pulse of brightness, appears to travel at a reduced speed, even though the underlying photon has not actually decelerated. It is like a traveler who walks at the same pace but must stop at every door to exchange a word with the people inside. The journey takes longer, but the walking speed never changed. And the moment the light exits the material, the polariton dissolves and the photon emerges as it always was, pure, unburdened, and moving at the full and beautiful speed of light once more. Light travels through water at roughly 75% of its speed in a vacuum. This means that the wavefront of light, as it passes through the body of a lake or an ocean or even a glass of water on your nightstand, moves noticeably slower than it would in the emptiness between stars. The photons themselves are still photons, still massless, still fundamental, still faithful to their nature. But their passage through the dense web of water molecules creates that combined disturbance, that dance of light and matter, which carries the signal forward at a gentler pace. It is why light bends when it enters water, why a straw in a glass appears to break at the surface, why the world beneath a swimming pool shimmers and warps when seen from above. The slowing of light through water is one of the reasons our world looks the way it does. Soft, refracted, full of gentle distortions that make the ordinary feel dreamlike. Water does not trap light. It simply asks it to waltz before letting it go. Light moves through standard window glass at approximately 66% of its speed in a vacuum. This figure comes from the refractive index of ordinary glass, which is about 1.5, meaning light's wavefront moves about 1.5 times slower through glass than through empty space. But glass is a broad and varied family of materials, and not all glass treats light the same way. Dense lead flint glass, the kind sometimes used in fine crystal or specialized optics, has a refractive index closer to 1.9, which means it can slow the wavefront of light down to roughly 50% of its vacuum speed. The photons passing through are unchanged. They are still themselves, still carrying their energy, still vibrating at their original frequency. But the medium they are passing through shapes the journey, the way a thick forest shapes the path of the wind, and when they emerge on the other side, they emerge whole, restored, traveling once again at the one true speed that light has always known. In 1999, a physicist named Lena Howe and her team at Harvard achieved something that seemed almost impossible. They slowed the wavefront of light to just 17 meters per second. To put that in perspective, that is slower than a bicycle. They accomplished this by passing light through an extraordinary state of matter called a Bose-Einstein condensate, which is a cloud of sodium atoms cooled to just a fraction of a degree above absolute zero. At such extreme cold, the atoms behave in strange and collective ways, and the interaction between the light and this ultra-cold medium produced a polariton that crawled forward at a pace the universe had never seen before. But Howe's team did not stop there. In 2001, they went even further. They brought the wavefront of light to a complete stop, holding it suspended in the condensate for a fraction of a second before releasing it to continue on its way. Light, the fastest thing in the universe, was made to pause. It is one of the most breathtaking experiments in the history of physics, a moment when human ingenuity asked light to be still, and light, for just an instant, obliged. Photons travel in straight lines unless something deflects them: gravity, refraction, or reflection. In the emptiness of space, far from any star or planet or cloud of dust, a photon will move in a perfectly straight path forever, never curving, never wavering, never drifting from the line it was born to follow. But the universe is not empty. It is full of matter and energy and the warping of space itself, and all of these things can bend the path of light. A massive object like a star or a black hole curves the fabric of space around it, and a photon passing through that curved space follows the curve, not because it has been pushed, but because the road itself has changed shape. A prism bends light through refraction. A mirror bends it through reflection. And in each case, the photon simply follows the geometry of the world it is moving through, obedient to the shape of space and the nature of the surfaces it encounters. Light does not resist. It does not argue. It simply goes where the universe asks it to go, as graceful and uncomplaining as water flowing downhill. From the perspective of a photon, time does not pass. According to Einstein's theory of special relativity, as an object approaches the speed of light, time for that object slows down relative to a stationary observer. And at the speed of light itself, the speed at which every photon travels, time stops entirely. This means that from the photon's own frame of reference, the moment of its creation and the moment of its absorption are one and the same. A photon born in the heart of a star 8 billion light years away and absorbed by a telescope on Earth tonight experienced no journey at all. For the photon, there was no waiting, no patience, no long passage through the dark. There was only a single instantaneous moment, a flash of existence in which birth and arrival were the same breath. It is a truth that sits at the edge of what the human mind can hold. This idea that the light falling on your closed eyelids right now has, from its own point of view, never traveled at all. Photons do not decay on their own. A photon traveling through perfectly empty space can exist indefinitely, carrying its energy forward without loss, without weakening, without slowly fading like a voice growing faint in the distance. Most particles in the universe have a limited lifespan. They break down, they transform, they release their energy and become something else. But the photon is not bound by such rules. It is stable, permanent, enduring in a way that almost nothing else in nature can claim. A photon released 1 billion years ago, if it has encountered nothing along its path, is just as whole and just as bright as the moment it was born. It has not aged, it has not tired. It has simply traveled, carrying its tiny cargo of energy through the silence of space with a faithfulness that borders on devotion. In a universe where everything changes, the photon is a rare and beautiful constant, a traveler that never wears out, a light that never dims on its own. A photon can travel across the entire observable universe without aging or degrading, as long as it encounters nothing along the way. The observable universe stretches approximately 93 billion light-years from one edge to the other, a distance so vast that the mind cannot truly hold it. And yet, a single photon, weightless and tireless, is capable of crossing that entire expanse without losing a single fraction of its original energy. It would not slow down. It would not fade. It would arrive at the far end of the cosmos carrying the same frequency, the same wavelength, the same quiet vitality it had at the beginning. This is the astonishing endurance of light. It does not consume fuel. It does not deplete itself. It does not spend anything to keep moving. It simply is, and it simply goes, and in the going it remains perfectly and completely itself. The darkness of space is no obstacle to a photon. It is merely the road, and the photon walks it without ever growing weary. The direction a photon travels is determined at the moment of its creation. When an electron inside an atom drops from a higher energy state to a lower one, or when a nuclear reaction deep inside a star releases a burst of radiance, the photon that is born in that instant is already aimed. It already knows where it is going, not because it has a mind or a will, but because the conditions of its birth set its course the way a hand sets the course of an arrow. Once released, a photon does not wander. It does not search for a path. It moves in the direction it was given, and it holds that direction with absolute steadiness unless something, a gravitational field, a surface, a lens, a raindrop, intervenes to change its course. There is something deeply peaceful about this. The photon does not choose, it does not hesitate. It is sent and it goes, and in going it carries out the quiet and eternal work of light, delivering energy from one place to another across the vast and silent distances of the universe. The color of light is determined by the wavelength of its photons. Every photon vibrates as it moves, rising and falling in a rhythm that is uniquely its own, and the distance between one crest of that vibration and the next is what we call the wavelength. When that wavelength is long and slow, the light appears red. When it is short and quick, the light appears violet. And between those two extremes lies the entire visible spectrum, the oranges and yellows, the greens and blues, the soft indigos that paint the sky at dusk. Color is not a thing that exists out in the world on its own. It is a relationship between a photon and your eye, a conversation between a wavelength and the delicate cells inside your retina. The rose is not red because redness lives in its petals. It is red because the photons it reflects have a wavelength that your brain interprets as red. Color is the way your mind translates the music of light into something you can see, and every hue you have ever loved is a wavelength singing. Red light has the longest wavelength in the visible spectrum, stretching to approximately 700 nanometers. A nanometer is a unit of measurement so small that it takes a billion of them to make a single meter, and yet within that tiny scale, enormous differences in color are born. At 700 nanometers, the vibration of a photon is slow and languid, like a deep note played on a cello, and your eye receives it as the warm, heavy color of embers and autumn leaves and the last light of evening. Red is the gentlest visible light in terms of energy. Its photons carry the least of all the colors your eyes can see. And perhaps that is why red feels warm, why it is the color of firelight and candlelight and the soft glow of a room at rest. It is the color of light at its most relaxed, its most unhurried, its most willing to linger. When you see red, you are seeing a photon at its longest, slowest, most meditative pace, a wave that takes its time, a rhythm that does not rush. Violet light has the shortest wavelength in the visible spectrum, arriving at approximately 380 nanometers. Where red light moves in long, slow waves, violet light vibrates rapidly, its crests packed closely together like quick, shimmering breaths. This means violet photons carry more energy than any other color your eye can see. They are the most vigorous, the most spirited, the most eager members of the visible family. And yet, despite that extra energy, violet is a color that often feels quiet. It lives at the far edge of what the human eye can detect, a color that borders on the invisible, that shimmers at the threshold between the seen and the unseen. Violet is the last color you can perceive before light passes beyond your ability to see it, crossing over into the ultraviolet realm that is hidden from your eyes, but not from the universe. There is something tender about violet. It is the color of transition, the color of the boundary between the known and the unknown, the last visible note before the song of light continues in frequencies only instruments can hear. A photon's energy is inversely proportional to its wavelength, which means that the shorter the wavelength, the more energy the photon carries, and the longer the wavelength, the less. This relationship is one of the fundamental truths of light, a quiet law that governs every color, every ray, every shimmer of brightness in the universe. A photon of violet light, with its short, tightly packed waves, carries nearly twice the energy of a photon of red light with its long, leisurely rhythm. And beyond the visible spectrum, the pattern continues. Ultraviolet photons carry more energy still, and X-ray photons carry even more, and gamma-ray photons, with wavelengths shorter than the width of an atom, carry the most energy of all. It is a beautiful and orderly relationship, this link between the size of a wave and the strength of what it carries. The universe has arranged its light on a spectrum from gentle to powerful, from the long, soft waves of radio to the short, fierce waves of gamma radiation, and every photon knows its place in that grand and quiet continuum. The relationship between a photon's energy and its frequency is described by one of the most elegant ideas in all of physics. It tells us that the energy of a photon is equal to its frequency multiplied by a very small, very specific number known as Planck's constant. Frequency is simply how many times a photon's wave crests in a single second, how quickly it vibrates, how fast its rhythm pulses. And Planck's constant is a fixed value, a number that never changes, a universal conversion factor that translates the speed of a vibration into the energy it carries. What this means, in the simplest and most beautiful terms, is that the faster a photon vibrates, the more energy it holds. A photon of blue light vibrates faster than a photon of red light, and so it carries more energy. A photon of X-ray radiation vibrates faster still, and so it carries far more. The universe tied energy to rhythm, to frequency, to the heartbeat of each individual photon, and it did so with a single, unchanging constant, a number so small and so precise that it feels like a secret whispered by the cosmos itself. Planck's constant is one of the most fundamental numbers in all of physics. It is an extraordinarily tiny value, a decimal point followed by 33 zeros before the first meaningful digit even appears. This number is the bridge between the world of waves and the world of energy. It is the key that unlocks the quantum realm, the conversion factor that tells you how much energy is carried by a single vibration of light. Max Planck discovered this constant at the turn of the 20th century, and it bears his name as a tribute to the moment when human understanding took a great and quiet leap forward. Without this number, we would have no quantum mechanics. Without it, we could not explain how atoms emit light, how semiconductors work, how the chemistry of life unfolds at the molecular level. It is a small number, impossibly small, and yet it holds the door open to an entire universe of understanding. Planck's constant is the heartbeat of the quantum world, and it pulses through every photon that has ever existed. White light is not a single color at all. It is a mixture, a blend of photons at many different visible wavelengths arriving at your eye together all at once in a chorus so seamless that your brain perceives it as a single, unified brightness. When you see white light, you are actually seeing red and orange and yellow and green and blue and violet all layered on top of one another, merged into something that appears colorless precisely because it contains all colors. It is one of the quiet miracles of perception that the presence of everything can look like the absence of anything. Sunlight is white for this reason. The light from an ordinary bulb is white for this reason. The soft glow of a cloudy sky is white for this reason. In each case, the photons arriving at your eye span the full visible spectrum, and your brain, rather than sorting them into individual colors, blends them into a single, gentle wash of brightness. White light is the sound of every instrument in the orchestra playing at once. Not chaos, but harmony, a chord so full it feels like silence. When white light passes through a prism, something quietly magnificent happens. The light separates into its individual wavelengths, revealing the hidden colors that were blended together all along. The prism does not add color to the light. It does not create anything new. It simply takes what was already there and fans it open, the way you might spread the pages of a closed book to reveal the words inside. Each wavelength of light bends by a slightly different amount as it passes through the glass, because the refractive index of the prism varies with wavelength. Red light, with its long, slow waves, bends the least. Violet light, with its short, quick waves, bends the most. And between them, every other color falls into place. Orange beside red, yellow beside orange, green beside yellow, blue beside green, indigo beside blue, violet at the far edge. What emerges is a spectrum, a ribbon of color that contains the entire story of visible light laid out in order, from the gentlest energy to the most spirited. A prism does not create a rainbow. It reveals one that was hiding in the light all along. Isaac Newton was the first to demonstrate this separation of white light using a glass prism in the year 1666. In a darkened room at Trinity College in Cambridge, he allowed a narrow beam of sunlight to enter through a small hole in a window shutter, and he placed a glass prism in the path of that beam. What emerged on the other side was not a simple spot of white light, but a long, vivid band of colors, red at one end, violet at the other, and every hue between. Newton called this band a spectrum, borrowing a Latin word that means appearance or apparition, and with that single experiment he overturned centuries of belief about the nature of light. Before Newton, most people believed that white light was pure and that colors were somehow added to it by the objects it touched. Newton proved the opposite, that white light was already a mixture, and that colors were not additions but components, not impurities but ingredients. He took the simplest thing in the world, a beam of sunlight, and showed that it held a hidden universe of color within it, waiting to be seen. A rainbow is one of the most beautiful natural demonstrations of what happens when light is refracted, reflected, and dispersed. When sunlight enters a raindrop, it slows down slightly and bends. This is refraction. Inside the drop, the light bounces off the far inner surface. This is reflection. And as the light exits the drop, it bends again, and because each wavelength bends by a slightly different amount, the white light fans open into its individual colors. This is dispersion. Every single raindrop in the sky performs this exact sequence, but your eyes can only catch the light from drops at a very specific angle, roughly 42 degrees from the point opposite the sun. This is why a rainbow is always an arc, always at the same angle, always following you as you move. Each color reaches your eye from a slightly different set of drops. The red from drops higher in the sky, the violet from drops lower down. A rainbow is not a fixed object hanging in the air. It is a personal performance, a private arrangement of light made just for your eyes, built from a million tiny prisms falling gently through the sky. The visible spectrum, the range of light that human eyes can detect, represents only a tiny fraction of the full electromagnetic spectrum. If you could stretch the entire electromagnetic spectrum out like a road, the portion visible to your eyes would be no wider than a single footstep on a path that stretches from one side of the country to the other. Our eyes evolved to see only a narrow band of wavelengths, roughly from 380 nanometers to 700 nanometers, and everything outside that band is invisible to us. Below the violet end, there is ultraviolet light, which causes sunburns but which we cannot see. Beyond ultraviolet, there are X-rays, which pass through skin and muscle. And beyond those, there are gamma rays, the most energetic photons of all. On the other side, beyond red, there is infrared light, the warmth you feel radiating from a fire but cannot see. And then microwaves, and then radio waves, stretching to wavelengths longer than football fields. All of these are photons. All of them are light. The only difference is the wavelength, and we are blind to almost all of it, seeing only the smallest sliver of the universe's full radiance. Beyond visible light, the electromagnetic spectrum includes radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays, and every single one of these is made of photons. They are all the same fundamental particle, the same massless messenger, the same quantum of electromagnetic energy. The only thing that distinguishes one from another is the wavelength, the distance between the crests of its wave. Radio photons have wavelengths that can stretch for miles, long and slow and gentle, carrying music and voices across entire continents. Microwave photons are shorter, warm enough to heat food and transmit signals from satellites. Infrared photons are the warmth of your own body, the silent glow that every living thing emits. Ultraviolet photons carry enough energy to damage skin, but also to help your body produce vitamin D. X-ray photons can pass through flesh and reveal the bones beneath. And gamma-ray photons, the shortest and most powerful of all, are born in the hearts of exploding stars and the collision of atoms. They are all the same particle. They are all light. The universe simply plays them at different frequencies, the way a single instrument can play every note. Photons are born inside atoms. When an electron orbiting an atom's nucleus drops from a higher energy level to a lower one, the energy it loses does not simply vanish, it is released as a photon. The electron falls, and in falling, it gives birth to a tiny particle of light whose energy precisely matches the energy the electron surrendered. It is a beautifully exact exchange. Nothing is lost, nothing is wasted, nothing is left over. The photon carries away exactly the amount of energy the electron no longer needs, like a sigh made visible. This is one of the most common ways that light enters the world, through the quiet rearrangement of electrons inside atoms, the gentle settling of charged particles from one orbit to another. It happens inside the sun, inside the filament of every light bulb, inside the glowing gas of a neon sign. Every time an electron falls, a photon rises. It is the fundamental transaction of light, the smallest and most ancient act of illumination. repeated trillions of times every second across the entire universe. This process, in which an excited electron drops to a lower energy level and releases a photon, is called spontaneous emission. The word spontaneous is important. No outside force tells the electron when to fall. No signal arrives to trigger the release. The electron simply decides in its own quantum way that the time has come to let go of its extra energy, and it does so by creating a photon. It is one of the most natural events in the universe, as natural as a leaf falling from a tree, as effortless as a drop of water releasing from the lip of a fountain, and the photon that is born in that moment carries with it all the information about the transition. Its wavelength tells you exactly which energy levels the electron moved between, its direction is set by the conditions of its birth, its polarization is determined by the geometry of the atom. Spontaneous emission is the universe breathing out light, and it happens everywhere, all the time. In every atom that has energy to spare, in every corner of the cosmos where matter is warm enough to glow. Every star in the sky, including our own sun, generates photons through nuclear fusion reactions in its core. Deep inside a star, where temperatures reach millions of degrees and pressures crush atoms together with unimaginable force, hydrogen nuclei are fused into helium, and in the process, a tiny fraction of their mass is converted into pure energy, energy that takes the form of photons. These photons are born in the innermost heart of the star, in a region so dense and so hot that light itself cannot move freely. A photon born at the center of the sun does not simply fly outward to the surface. It is absorbed and re-emitted by the surrounding matter over and over again, bouncing and scattering in a slow, random walk that can take hundreds of thousands of years to complete. When a photon finally reaches the sun's surface and escapes into space, it has been on a journey longer than the age of most civilizations. And then, in just 8 minutes, it crosses the distance to Earth and lands gently on the world below. The sun emits an almost incomprehensible amount of energy in the form of photons. Its total luminosity, the total power of all the light it sends out in every direction, is approximately 3.8 times 10 to the 26th power watts. That number is so large it resists meaning. It is hundreds of trillions of watts, pouring outward in every direction, filling the solar system with light and warmth and the energy that drives the wind, the rain, the tides of life on Earth. And yet the Earth intercepts only a tiny fraction of that output. Less than 1/1000th of the sun's total light falls on our small planet. The rest streams past us into the deep void of space, lighting nothing, warming nothing, traveling forever into the darkness between the stars. It is a humbling thought that the sunlight you feel on your face is the smallest sip from the most enormous fountain, and that the vast majority of the sun's generosity passes through our neighborhood entirely unnoticed, continuing its quiet journey toward the farthest edges of the cosmos. A single 100-watt incandescent light bulb emits roughly 1 billion trillion visible photons every second. That number, 10 to the 21st power, is so vast that no human mind can picture it. And yet it is the reality of something as ordinary as a lamp beside your bed. Each of those photons is a whole individual particle of light, born from the white-hot filament inside the bulb, carrying its own wavelength, its own energy, its own tiny share of the glow that fills the room. They pour outward in every direction, a silent and ceaseless flood of light particles that bathe the walls and the furniture and the sleeping faces of everyone nearby. And yet, because each individual photon carries such an incredibly small amount of energy, you never feel them arrive. They land on your skin by the trillions and you feel only warmth. They enter your eyes by the billions and you see only a gentle, steady glow. The extraordinary quantity of photons in even the most ordinary light is one of the quiet marvels of everyday life, an ocean of light flowing from a source no bigger than your thumb. Every object in the universe that has a temperature above absolute zero emits photons. This is a truth so all-encompassing that it includes everything you have ever seen, touched, or stood beside, including your own body. Absolute zero is the coldest anything can possibly be, the point at which all thermal motion ceases and nothing in the known universe has ever quite reached it. Everything is warmer than absolute zero, even the empty space between galaxies, and so everything radiates. A stone wall radiates infrared photons. A cup of tea radiates them more strongly. A bonfire radiates them in the visible range, which is why you can see its glow. The hotter an object is, the shorter the wavelengths of the photons it emits, and the more energetic those photons become. At room temperature, the photons you emit are in the infrared, invisible to your eyes but perfectly real, perfectly present, streaming softly from your skin like a quiet glow that only certain instruments can see. You are, right now, a source of light. Faint, gentle, invisible light, but light nonetheless. The human body emits photons in the infrared range because your body is warm, roughly 37 degrees Celsius or 98.6 degrees Fahrenheit, and anything warm radiates. These infrared photons are invisible to the naked eye, but they are absolutely real. They stream from your skin constantly, carrying tiny amounts of thermal energy out into the air around you. Infrared cameras can detect these photons and translate them into images. This is how thermal imaging works, painting a portrait of you made entirely from the light your own body produces. In such an image, you glow. Your face is bright, your hands are bright, and the blood flowing close to the surface of your skin creates a map of warmth and radiance that is uniquely yours. It is a quiet and remarkable truth that even in total darkness, even with every lamp extinguished and every screen turned off, you are never truly in the dark. Your body is always emitting light, always glowing softly in a spectrum just beyond what your eyes were built to see. You carry your own lantern, and it never goes out. Fire produces visible photons because of a process called incandescence, the thermal excitation of atoms and molecules at high temperatures. When something burns, the chemical reactions involved release a great deal of heat, and that heat causes the atoms in the flame and the surrounding material to vibrate with extraordinary intensity. These violently vibrating atoms emit photons across a broad range of wavelengths, and when the temperature is high enough, some of those wavelengths fall within the visible spectrum, which is why you can see the flame. The color of the fire tells you about its temperature. The deep red glow of cooling embers comes from photons at the long wavelength end of the visible range, produced at relatively lower temperatures. The bright yellow of a candle flame comes from slightly hotter regions, and the blue base of a gas flame, where the combustion is most intense, comes from the shortest visible wavelengths, where the photons carry the most energy. Fire is, in the deepest sense, a conversation between heat and light, a place where thermal energy is translated into visible photons, and where the language of that translation is written in color. Bioluminescent organisms, fireflies, certain jellyfish, deep sea fish, and many others, produce photons not through heat, but through chemistry. Inside their bodies, specific molecules undergo chemical reactions that release energy in the form of visible light. In the case of a firefly, a molecule called luciferin reacts with oxygen in the presence of an enzyme called luciferase, and the product of that reaction is a photon, a tiny flash of cold living light. It is called cold light because, unlike fire or an incandescent bulb, almost no heat is produced. Nearly all of the chemical energy is converted directly into light, making bioluminescence one of the most efficient forms of illumination in nature. Deep beneath the ocean's surface, where sunlight cannot reach, entire ecosystems are lit by this living glow. Fish with lanterns beneath their eyes, jellyfish that pulse with blue-green radiance, bacteria that coat the bodies of other creatures in shimmering mantles of light. Bioluminescence is the universe's reminder that light does not belong only to stars and fires. It belongs to life too, and life has learned to make its own. All LEDs, light-emitting diodes, produce photons through a process called electroluminescence. Inside an LED, electrons move through a semiconductor material and encounter a junction where two different types of semiconductor meet. When an electron crosses this junction, it falls into a lower energy state and releases the excess energy as a photon. The color of the photon depends on the specific semiconductor materials used. Different materials produce different wavelengths of light, which is why LEDs can glow in virtually any color. This process is remarkably efficient. Unlike incandescent bulbs, which waste most of their energy as heat, LEDs convert a much larger portion of their electrical energy directly into photons. They run cool. They last for tens of thousands of hours. They are, in many ways, the most civilized light sources humanity has ever created, producing illumination with minimal waste, minimal heat, and maximum gentleness. The soft glow of an LED beside your bed tonight is the result of electrons quietly surrendering their energy at a tiny junction, one photon at a time, in a rhythm so fast and so steady that the light appears perfectly smooth and unbroken. Lasers produce photons through a process called stimulated emission, a mechanism first described theoretically by Albert Einstein in 1917. Stimulated emission is different from spontaneous emission in a beautifully precise way. In spontaneous emission, an excited atom releases a photon on its own, at a random time and in a random direction. But in stimulated emission, an incoming photon passes close to an excited atom and coaxes it into releasing its stored energy as a second photon, a photon that is identical to the first in every way. Same wavelength, same direction, same phase, same polarization. The two photons emerge together, perfectly synchronized, like two voices singing the same note at the same moment with the same breath. This is how a laser builds its extraordinary beam, by triggering a cascade of identical photons, each one stimulating another until millions upon millions of perfectly matched photons are marching together in lockstep. The result is a beam of light so coherent, so unified, so perfectly organized that it can travel enormous distances without spreading or carry information with extraordinary precision. A laser is an orchestra in which every musician plays the same note at the same time, forever. In stimulated emission, the photon that arrives and the photon that is released are identical. They share the same wavelength, the same direction of travel, and the same phase, meaning their waves rise and fall in perfect unison, crest for crest, trough for trough. This is the key to understanding why laser light is so different from ordinary light. The light from a lamp or a candle is made of photons that are all jumbled together. Different wavelengths, different directions, different phases, each one going its own way like a crowd of people walking through a busy street. But laser light is made of photons that are all doing the same thing at the same time, a parade instead of a crowd, a chorus instead of noise. This coherence, this perfect agreement among photons, gives laser light its remarkable properties. It can be focused to an incredibly small point. It can be sent over vast distances without scattering. It can encode information with extraordinary fidelity, all because of the simple, elegant rule of stimulated emission, that one photon can call another into being and the second will be an exact and perfect echo of the first. The oldest photons in the universe are those of the cosmic microwave background radiation. They were released roughly 380,000 years after the Big Bang, at the moment when the universe had cooled just enough for atoms to form and for light to finally travel freely through space. Before that moment, the entire cosmos was a dense, opaque fog of charged particles, electrons and protons so tightly packed that photons could not move more than a short distance before being scattered in a new direction. But when the temperature dropped below a critical threshold, those particles combined into neutral atoms, and suddenly the fog lifted. The photons that had been trapped were set free, released into a universe that had just become transparent for the first time. Those photons have been traveling ever since, for approximately 13.8 billion years, and they still fill the entire observable universe, arriving from every direction in the sky like a soft, eternal whisper from the beginning of time. They are the oldest light you will ever encounter, a message from the infancy of everything. The cosmic microwave background was discovered accidentally in 1965 by two radio astronomers named Arno Penzias and Robert Wilson, who were working at Bell Telephone Laboratories in New Jersey. They were using a large horn-shaped antenna designed for satellite communications, and no matter what they did, they could not eliminate a persistent, low-level hiss of microwave radiation coming from every direction in the sky. They checked their equipment, they cleaned the antenna, they even removed a family of pigeons that had been nesting inside it. But the noise remained, constant, uniform, and utterly mysterious. It was not coming from the Earth. It was not coming from the Sun. It was coming from everywhere. Eventually, they learned that a group of physicists at nearby Princeton University had predicted that exactly this kind of radiation should exist. A faint afterglow of the Big Bang, stretched by the expansion of the universe into the microwave range. Penzias and Wilson had stumbled upon the oldest light in the cosmos, and for this discovery they were awarded the Nobel Prize in Physics. The photons of the cosmic microwave background have been traveling for approximately 13.8 billion years, and they now fill the entire observable universe. There is no place you can point a radio telescope where these photons are not present. They arrive from every direction with almost perfect uniformity, carrying a nearly identical temperature no matter where in the sky you look. This uniformity is itself a profound clue about the early universe. It tells us that the cosmos, at the time these photons were released, was remarkably smooth and even, with matter and energy distributed almost perfectly in every direction. These ancient photons have been stretched by the expansion of the universe during their long journey, their wavelengths growing longer and longer as the fabric of space itself has expanded. What began as a hot, bright glow has become a cold, faint whisper in the microwave range, invisible to the human eye but detectable by the right instruments. They are the background hum of creation, the quietest and most enduring sound the universe has ever made. The cosmic microwave background has a temperature of about 2.725 Kelvin, which is just a few degrees above absolute zero, the coldest possible temperature in the universe. This is the temperature of the oldest light in existence, and it is astonishing in its coldness. When these photons were first released, they were blisteringly hot. The universe at that time had a temperature of roughly 3000 Kelvin, hot enough to glow with a bright orange-red light visible to the naked eye. But in the 13.8 billion years since then, the expansion of the universe has stretched these photons enormously, cooling them down to the faint, frigid whisper they are today. From a blazing glow to a cold murmur in the microwave range. That is the story of the cosmic microwave background. And yet, even at this incredibly low temperature, these photons are not nothing. They carry energy. They carry information. They carry the memory of a moment when the universe was young and hot and just beginning to become the place we know. They are the gentlest remnants of the most violent beginning. Before the cosmic microwave background was released, the early universe was completely opaque. Photons could not travel freely because they were constantly scattered by free electrons, charged particles that had not yet combined with nuclei to form neutral atoms. Imagine a fog so thick that light can only travel a tiny distance before being deflected in a random direction, over and over and over again. That was the state of the entire universe for the first 380,000 years of its existence, a seething, blinding fog of plasma in which light was trapped, unable to carry a message more than a fraction of a distance. The universe was full of light, but none of it could go anywhere. It was brightness without vision, energy without freedom. And then, as the universe expanded and cooled, the electrons finally slowed down enough to be captured by atomic nuclei, and the fog cleared. The universe became transparent, and the photons that had been bouncing aimlessly were suddenly free to stream forward into the newborn emptiness. That moment of liberation is what we see today as the cosmic microwave background. The moment when the universe became transparent enough for photons to travel freely is called recombination. It is a slightly misleading name because it suggests that electrons and nuclei were combining again, recombining, when in fact they were combining for the very first time. Before this moment, the universe was too hot for stable atoms to exist. Electrons and protons flew about separately as a plasma, and photons were trapped in the chaos. But as the universe expanded and the temperature fell below roughly 3000 Kelvin, electrons began to settle into orbit around nuclei, forming the first neutral atoms, mostly hydrogen and helium. With the free electrons now bound within atoms, there was nothing left to scatter the photons, and light was finally free. Recombination was not a dramatic explosion or a visible event. It was a quiet threshold, a gentle crossing of a line, a moment when the universe simply became clear. It is the oldest horizon we can see, the farthest back in time that light allows us to look. Everything before recombination is hidden behind a wall of fog, and everything after it is illuminated by the photons that have been traveling toward us ever since. Light from the sun takes approximately 8 minutes and 20 seconds to reach Earth. This means that when you look up at the sun, or rather when you feel its warmth on your closed eyes, you are experiencing light that left the sun's surface over 8 minutes ago. You are not seeing the sun as it is now. You are seeing it as it was in the very recent past. A past so close it feels like the present, but is, in truth, already gone. Those photons that warm your face began their journey across 93 million miles of empty space while you were still doing whatever you were doing 8 minutes ago, and they have been flying toward you at the speed of light ever since. It is a small delay, barely noticeable in the rhythm of a human day, and yet it contains a profound truth, that all light is a time traveler, that every photon you see is a messenger from the past, and that even the most familiar light in the sky is showing you something that has already happened. The sun you see is always a memory, always 8 minutes old, always a gentle echo arriving from across the silence. The nearest star system to the sun is Alpha Centauri, and it sits approximately 4.37 light-years away. This means that the light leaving Alpha Centauri tonight will not reach Earth for more than 4 years. When you look up at a dark sky and find that star, if you are far enough south to see it, you are not seeing it as it is now. You are seeing it as it was 4 years ago, bathed in the light of a past you cannot touch. And Alpha Centauri is our nearest neighbor. It is the closest star outside our own solar system, the first step beyond the front door, and even it is so far away that its light takes years to arrive. The distances between stars are almost inconceivably vast, and light, the fastest thing in the universe, is the only messenger patient enough to cross them. Every star you see in the night sky is a postcard from the past, written in light, delivered across years or decades or centuries. The sky is not a picture of the present. It is a mosaic of countless different pasts, each one arriving on the wings of photons that have been flying since before you were born. The light we see from distant galaxies may have been traveling for millions or even billions of years before reaching our eyes. When astronomers point a telescope at a far-off galaxy and capture its light, they are not seeing that galaxy as it exists today. They are seeing it as it existed when that light was first emitted, in an era that may predate the formation of Earth itself. A galaxy 1 billion light-years away is seen as it was 1 billion years ago. A galaxy 10 billion light-years away is seen as it was 10 billion years ago, when the universe was young, when stars were just beginning to organize themselves into the shapes and patterns we recognize. This is the extraordinary power of light as a tool for understanding the cosmos. It is a time machine. Every photon carries a timestamp, a record of the moment it was born, and by collecting photons from farther and farther away, we can look deeper and deeper into the past. The telescope is not just a lens, it is a window into history, and every distant galaxy is a chapter in the autobiography of the universe, written in light and delivered across the silence of space. As the universe expands, something poetic happens to the photons traveling through it. Their wavelengths stretch. This phenomenon is known as cosmological redshift, and it is one of the most important discoveries in the history of astronomy. As a photon journeys across the cosmos, the very fabric of space through which it travels is expanding, and this expansion gently pulls the photon's wavelength longer, the way stretching a rubber band would lengthen a line drawn upon it. A photon that was born as visible light in a distant galaxy may arrive at Earth billions of years later with its wavelength stretched into the infrared or even the microwave range. It is the same photon carrying the same fundamental identity, but the universe has reshaped it during the journey. The amount of redshift tells astronomers how much the universe has expanded since that photon was emitted, which in turn reveals how far away the source is and how long the light has been traveling. Cosmological redshift is the universe writing its own history in the wavelengths of light, and every stretched photon is a word in that quiet, ongoing story. Cosmological redshift allows astronomers to determine how fast distant objects are moving away from us and how far away they are. When a galaxy's light is more redshifted, when its wavelengths have been stretched more, it means that the space between us and that galaxy has expanded more, which means the galaxy is farther away and its light has been traveling for a longer time. This relationship between redshift and distance is one of the foundational tools of modern cosmology. It was first observed by astronomer Edwin Hubble in 1929 when he noticed that almost every galaxy he studied showed a redshift, and that the more distant galaxies were more redshifted than the closer ones. This led to one of the most important conclusions in the history of science, that the universe is expanding. Every galaxy is moving away from every other galaxy, not because they are flying through space, but because the space between them is growing. And we know this because of photons, because the light from those galaxies carries within its wavelength a quiet, measurable record of how much the universe has stretched since the light began its journey. Some photons in the universe will never reach us. The universe is expanding, and in many regions of space, the rate of that expansion is so great that the space between a distant photon and the Earth is growing faster than the photon can cross it. This is not a violation of the speed of light. The photon is still traveling at the full speed of light through its local patch of space, but the space itself is stretching so rapidly that the photon falls farther behind with every passing moment, like a swimmer in a river whose current is faster than their stroke. These photons are out there, real and whole, and carrying their energy faithfully, but they will never arrive. They will travel forever without reaching us, lost in the expanding distance between their origin and our small corner of the cosmos. It is a quietly astonishing thought that there are regions of the universe whose light we will never see, no matter how long we wait, no matter how powerful our telescopes become. The visible universe has an edge, not because the cosmos ends, but because light from beyond that edge can never outrun the expansion of the space between us. Photons carry information. Nearly everything we know about distant stars, about the composition of faraway galaxies, about the temperature of the cosmic microwave background, about the age and shape and fate of the universe. All of it comes from analyzing photons. Light is not just illumination, it is communication. Every photon that arrives at a telescope or a camera or a human eye carries within it a record of its origin. Its wavelength tells us what produced it. Its intensity tells us how much energy was released. Its redshift tells us how far it has traveled, and the way it has been absorbed or scattered along the way tells us about everything it passed through on its journey. Astronomy is, at its heart, the science of reading photons, of collecting these tiny messengers and decoding the stories they carry. We have never touched a star. We have never visited another galaxy. We have never held a piece of the cosmic microwave background in our hands. And yet we know astonishing things about all of them because the light told us. Photons are the universe's letters, and the sky is the mailbox, and every night the cosmos sends us more. Spectroscopy is the study of how matter interacts with light, and it is one of the most powerful tools in all of science. When light from a star or a galaxy passes through a prism or a diffraction grating, it spreads into a spectrum, a rainbow of wavelengths. And within that spectrum there are dark lines where certain wavelengths are missing. These lines are called absorption lines, and they appear because atoms in the star's outer layers have absorbed photons at very specific wavelengths that correspond to the energy levels of their electrons. Each element leaves a unique pattern of lines, like a fingerprint, and by reading these patterns, scientists can determine what a star is made of without ever visiting it. Spectroscopy can also reveal a star's temperature, its velocity, its magnetic field, and whether it has planets orbiting around it. All from light, all from photons arriving after journeys of years or centuries or millennia, carrying within their wavelengths the chemical identity of the place that sent them. It is one of the most beautiful collaborations in science, between the curiosity of human beings and the faithfulness of light. In the famous double-slit experiment, something deeply mysterious happens. When individual photons are sent one at a time toward a barrier with two narrow slits, and a screen is placed behind the barrier to record where they land, you would expect each photon to pass through one slit or the other and create two simple bands of light on the screen, but that is not what happens. Over time, as more and more photons arrive, they form an interference pattern, a series of bright and dark bands that only make sense if each photon somehow passed through both slits at the same time and interfered with itself. A single, indivisible particle of light passing through two openings at once and creating a pattern that only waves can make. It is one of the most baffling results in all of physics, a result that has been confirmed thousands of times and yet still sits at the edge of human understanding. The double-slit experiment reveals that a photon is not simply a particle traveling along a definite path. It is something stranger, something more fluid, something that carries within it the potential to be in more than one place at once. The double-slit experiment was first performed with light by a scientist named Thomas Young in the year 1801. Young was an English polymath, a physician, a physicist, and a linguist who helped decipher Egyptian hieroglyphics, and his experiment with light was one of the most elegant demonstrations in the history of science. He allowed sunlight to pass through a tiny pinhole, creating a narrow beam, and then directed that beam at a card with two thin slits cut close together. On a screen behind the card, he observed not two simple patches of light, but a pattern of alternating bright and dark bands. An interference pattern that could only be produced by waves overlapping and reinforcing or cancelling each other out. This was powerful evidence that light behaved as a wave, and it challenged the dominant view of the time, which held that light was made of tiny particles. Young's experiment settled the debate for over a century, until quantum physics came along and revealed that light is both, always both, a wave and a particle woven together in a duality that defies easy explanation. When a detector is placed at the slits to observe which slit a photon passes through, something remarkable and unsettling happens. The interference pattern disappears. The photons begin to behave like ordinary particles, passing through one slit or the other and forming two simple bands on the screen instead of the complex wave pattern they produced before. This is known as the observer effect, and it is one of the deepest mysteries in quantum physics. The act of measuring, of looking, of gathering information about the photon's path seems to change the photon's behavior. When no one is watching, the photon behaves as a wave, spreading through both slits and interfering with itself. When someone watches, it behaves as a particle, choosing a single path and abandoning its wave-like nature. It is not that the instrument disturbs the photon physically. The mystery runs deeper than that. It is as though the photon's nature is not fixed until it is observed, as though the universe holds its breath until a measurement is made and only then decides what reality will be. The observer effect is a gentle reminder that at the quantum level, the act of knowing and the act of being are not separate things. Quantum entanglement is a phenomenon in which two photons become linked in such a way that measuring a property of one photon instantly determines the corresponding property of the other, no matter how far apart they are. If two photons are entangled and you measure the polarization of one and find it to be vertical, you will know with absolute certainty that the other photon's polarization is horizontal, even if that second photon is on the other side of the galaxy. This connection is instantaneous. It does not depend on any signal traveling between the two photons. It does not obey the usual rules of cause and effect that govern the everyday world. It is as if the two photons, once entangled, are no longer truly separate. They are two halves of a single quantum system, sharing an identity that transcends distance. Entanglement does not transmit information faster than light, because the outcome of the measurement appears random. It is only when the two results are compared that the correlation becomes visible. But the connection itself is real, immediate, and one of the most profound mysteries the quantum world has to offer. Albert Einstein was famously uncomfortable with quantum entanglement. He called it spooky action at a distance, a phrase that has become one of the most quoted lines in the history of physics. Einstein accepted the mathematics of quantum mechanics, but he struggled with the idea that two particles could be connected in a way that seemed to ignore the constraints of space and time. He believed that something must be missing from the theory, that there must be hidden variables, unseen factors that determined the photon's properties in advance, the way a coin's outcome is determined by the physics of its flip, even if we cannot see the details. In 1935, Einstein co-authored a famous paper with Boris Podolsky and Nathan Rosen, arguing that quantum mechanics must be incomplete. But decades of subsequent experiments, beginning with those of John Bell in the 1960s and continuing to the present day, have consistently shown that entanglement is real, that no hidden variables can explain the results, and that the universe truly does allow this strange, non-local connection between distant particles. Einstein's discomfort was understandable. The universe turned out to be even stranger than he had hoped. In 2017, Chinese scientists used a satellite called Mikius to demonstrate quantum entanglement of photons over a distance of 1,200 kilometers. The satellite, named after an ancient Chinese philosopher, carried a source of entangled photon pairs in orbit above the Earth. It generated pairs of entangled photons and sent one photon from each pair to a ground station in one Chinese city and the other photon to a ground station in a different city more than 1,000 kilometers away. When the scientists measured the photons at both stations, the results confirmed that the quantum correlations were preserved. The entanglement had survived the journey through space, across a distance far greater than any previous experiment had achieved. This was a landmark achievement not just for physics, but for the emerging field of quantum communication, which aims to use entangled photons to create communication channels that are fundamentally secure against eavesdropping. The Messius experiment showed that the quantum connection between entangled photons is not fragile. It can survive the vastness of space, the passage through the atmosphere, and the immense distances between ground and sky. A photon's polarization describes the orientation of its electromagnetic wave as it oscillates. As a photon travels through space, its electric field vibrates in a particular direction, up and down, side to side, or at any angle in between. And this direction of vibration is what we call its polarization. You can think of it as the direction in which the photon's wave is waving, the way a jump rope can wave up and down or side to side depending on how you move your hand. Polarization is not something you can see with the naked eye under normal circumstances, but it is a real and measurable property of every photon. It determines how the photon interacts with certain materials, how it passes through certain filters, and how it can be used to encode information. Polarization is one of the most useful properties of light in technology. It plays a role in everything from sunglasses to television screens to the transmission of data through fiber optic cables. It is a quiet property, invisible to casual observation, and yet it shapes the way light moves through the world in ways both subtle and profound. Polarization can take several forms. Linear polarization means the electric field of the photon vibrates along a single straight line, up and down, or side to side, or at some fixed angle. Circular polarization means the electric field rotates as the photon travels, tracing a circle in the plane perpendicular to its direction of motion, like a corkscrew turning as it moves forward. And elliptical polarization is a blend of the two. The electric field traces an ellipse, a stretched circle, as it rotates. These different forms of polarization are not different kinds of photons. They are different states of the same fundamental particle, different ways for the same wave to move. A single photon can be linearly polarized, circularly polarized, or elliptically polarized, depending on how it was created or how it has interacted with materials along its path. The variety of polarization states gives light an extraordinary richness and versatility, a vocabulary of orientations and rotations that scientists and engineers have learned to read, write, and use in countless ways. Polarized sunglasses work by blocking photons with certain polarization orientations, reducing glare. When sunlight reflects off a flat surface like water, a road, or the hood of a car, the reflected light becomes partially polarized. Its electric field vibrates predominantly in the horizontal direction. This horizontally polarized light is what we experience as glare, that harsh, blinding brightness that makes it difficult to see. Polarized sunglasses contain a filter that is oriented to block horizontally polarized photons while allowing vertically polarized photons to pass through. The effect is remarkable. The glare vanishes, and the world appears clearer, softer, and more comfortable to look at. It is a beautiful example of how understanding a subtle property of photons, the direction of their waves' vibration, can be translated into something practical and everyday. Every time you put on a pair of polarized sunglasses and the glare disappears, you are experiencing a direct, personal encounter with the physics of polarization. A quiet interaction between your eyes and the hidden orientation of light. A single photon can exist in a superposition of polarization states until it is measured. This means that before any observation is made, the photon does not have a definite polarization. It exists in a kind of quantum blend, a combination of multiple possible orientations at once. It is not that we simply do not know its polarization. It is that the polarization is genuinely undetermined, hovering in a state of quantum potential until the moment of measurement collapses it into a single, definite outcome. This is one of the central and most counterintuitive ideas in quantum mechanics, that particles do not have fixed properties until those properties are observed. The photon in superposition is like a note that is both sharp and flat at the same time, or a coin that is both heads and tails until it is caught and looked at. It is the universe holding its options open, maintaining a quiet ambiguity that resolves only when the world insists on an answer. Superposition is not uncertainty born of ignorance. It is uncertainty woven into the fabric of reality itself. Photons are indistinguishable from one another when they share the same properties. No experiment, no matter how precise, can tell two photons apart if they have the same wavelength, the same polarization, the same direction of travel, and the same phase. They are not merely similar, they are identical in a way that has no parallel in the everyday world. Two red marbles may look alike, but under a microscope you could find tiny differences in their surfaces. Two photons with the same properties have no such differences. There is nothing hidden, nothing individual, nothing that marks one as distinct from the other. This indistinguishability is not a limitation of our instruments. It is a fundamental feature of reality. In quantum mechanics, swapping two identical photons produces no detectable change in the system whatsoever, as though the swap never happened. This property has deep consequences for how photons behave in groups and is one of the reasons laser light, in which enormous numbers of identical photons move together, has such unique and powerful properties. Photons are the ultimate ensemble players. They do not carry individual identities, and their power comes from their perfect, selfless sameness. Because photons are bosons, any number of them can occupy the same quantum state at the same time. This is what separates bosons from the other great family of particles, fermions, which include electrons and protons and are forbidden by the Pauli exclusion principle from sharing the same state. Photons have no such restriction. 100 photons can be in the same state. 1,000,000 can. 1,000,000,000,000 can. There is no limit, no crowding, no competition. This is the property that makes laser light possible. In a laser, enormous numbers of photons are coaxed into exactly the same quantum state, all with the same wavelength, direction, and phase, all moving in perfect unison. And because they are bosons, they are not just allowed to do this, they actually prefer it. The more photons that are already in a given state, the more likely it is that another photon will join them. It is a kind of quantum sociability, a tendency to gather together and move as one. This is why laser beams are so intense and so coherent. They are made of photons that have all chosen to be the same thing in the same place at the same time, and nothing in the laws of physics prevents it. Quantum electrodynamics, often abbreviated as QED, is the quantum field theory that describes how photons interact with electrically charged particles, such as electrons. It is one of the most successful and precisely tested theories in the entire history of science. QED explains every interaction between light and matter at the most fundamental level, how photons are emitted and absorbed, how electrons scatter when they encounter light, how the electromagnetic force operates at the quantum scale. The theory describes these interactions in terms of virtual photons, fleeting, temporary photons that pop into existence, mediate a force and then vanish, exchanged between charged particles in a continuous, invisible dance. QED predicts certain quantities with extraordinary precision. The magnetic moment of the electron, for example, has been calculated using QED to more than 10 decimal places and confirmed by experiment to the same degree. It is often said that QED is the most accurate theory ever devised by human beings, a description of the universe so precise that it borders on perfection. And at its heart, in every calculation and every prediction, is the photon, the carrier of the force, the mediator of the interaction, the thread that holds the theory together. QED was developed in the late 1940s by three physicists working independently: Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga. Each of them found a different mathematical approach to the same problem, and all three approaches turned out to be equivalent, producing identical predictions despite their different frameworks. For this remarkable achievement, all three shared the Nobel Prize in Physics in 1965. Feynman's approach is perhaps the most famous. He introduced a visual method of calculation called Feynman diagrams, which represent particle interactions as simple, elegant drawings. In a Feynman diagram, a photon is drawn as a wavy line, an electron as a straight line, and their interactions are shown as vertices where the lines meet. These diagrams are not just illustrations, They are precise mathematical tools that encode the probability of each interaction and allow physicists to calculate outcomes with stunning accuracy. QED is considered one of the crown jewels of theoretical physics, and the photon sits at its center, the particle that binds light and matter together, the quantum of the electromagnetic force, the smallest thread in the tapestry of everything that shines. Human vision begins when photons enter the eye and strike photoreceptor cells in the retina, specialized cells called rods and cones that have evolved over hundreds of millions of years to detect and respond to light. When a photon arrives at one of these cells, it is absorbed by a light-sensitive molecule called a photopigment, and the energy of that photon triggers a chemical change in the molecule that sends an electrical signal through the optic nerve to the brain. This is the beginning of sight, not in the brain, not in the mind, but in the retina, in the quiet moment when a photon gives up its energy to a molecule inside your eye. Cones are responsible for color vision. There are 3 types, sensitive to different ranges of wavelengths, and together they allow you to see the full spectrum of visible color. Rods are more sensitive to dim light and are responsible for your ability to see in the dark, though they do not perceive color. Every image you have ever seen, every face, every sunset, every word on a page began as photons landing on these tiny cells and whispering their arrival through chemistry and electricity to the waiting brain. Rod cells in the human eye are sensitive enough to respond to a single photon. This extraordinary sensitivity was long theorized, and in 2016 it was experimentally confirmed. A single rod cell can indeed absorb a single photon and generate a measurable electrical response. However, the story of human perception is slightly more nuanced than that. While an individual rod cell reacts to one photon, the brain does not register a conscious flash of light from a single photon alone. Instead, the brain requires a small threshold of several photons arriving in a short period before it acknowledges the signal as genuine light. This filtering exists for a remarkable reason. The eye produces its own internal noise, tiny false signals generated by the thermal energy of the molecules inside the retina. And if the brain responded to every single photon-level signal, it would be constantly perceiving faint flashes that were not really there. So the brain sets a threshold, a quiet standard, and only when enough photons arrive close together in time does it allow the perception of light to surface into consciousness. Your eyes are sensitive enough to detect a single particle of light, but your brain wisely waits for confirmation before it believes. Photosynthesis, the process by which plants convert sunlight into energy, depends entirely on photons. When a photon from the sun strikes a leaf, it can be absorbed by a molecule of chlorophyll embedded in the leaf's cells. The energy of that photon excites an electron within the chlorophyll molecule, raising it to a higher energy state, and that excited electron is then passed along a chain of molecular partners in a carefully orchestrated sequence of chemical reactions. The end result of this chain is the conversion of carbon dioxide and water into glucose, a sugar that the plant uses as food, and the release of oxygen as a byproduct. This is the chemistry that sustains nearly all life on Earth. The oxygen you are breathing right now was released by a plant that captured a photon and used its energy to split a water molecule. The food you ate today traces its energy back through one chain or another to photons that were absorbed by green leaves. Photosynthesis is the bridge between starlight and life, the process by which the energy of the sun becomes the energy of every living thing, and it begins with a photon landing on a leaf and whispering, "Grow." Chlorophyll, the pigment responsible for the green color of plants, absorbs photons most efficiently in the red and blue wavelengths of visible light and reflects green wavelengths back. This is why leaves appear green to your eyes. The green photons are the ones that the leaf does not use, the ones it sends away, the ones that bounce off the surface and travel to your retina. The colors a plant absorbs are the colors it consumes, and the color it shows you is the color it has no need for. There is something quietly poetic about this, that the color of a forest, the green that fills your vision when you walk among the trees, is the light that the leaves have rejected, the wavelength they found least useful. The energy that feeds the plant comes from the red and the blue, the photons at either end of the visible spectrum, while the green passes through or reflects away, unwanted by the chemistry of life but welcomed by the human eye. The beauty of a green leaf is made from the light it refused, and the life of the forest is made from the light you never see. Solar panels convert photons into electricity through a process known as the photovoltaic effect. When a photon strikes a semiconductor material in a solar cell, typically silicon, it can transfer its energy to an electron within the material, knocking that electron free from its atomic bond and allowing it to flow through an electrical circuit as current. This is a direct conversion of light into electricity, one photon at a time. The word photovoltaic itself tells the story, photo from the Greek for light, and voltaic from the Italian physicist Alessandro Volta, who pioneered the study of electrical potential. Not every photon that strikes a solar panel produces electricity. The photon must carry enough energy to dislodge an electron, and photons with too little energy pass through without effect. But when the match is right, when the photon's energy meets the electron's need, the result is a small but real flow of current. One electron set free by one photon, joining millions of others to power your home, your phone, the quiet machinery of modern life. Solar energy is, in the simplest sense, the harvesting of photons, the gathering of the sun's ancient messengers, and translating their gifts into the language of electricity. Fiber optic cables transmit information as pulses of photons through thin strands of glass, enabling high-speed internet and telecommunications across the globe. Each fiber is typically about the width of a human hair, and photons bounce along the interior of this slender thread by a process called total internal reflection. They strike the inner wall at such a shallow angle that they are reflected back into the core rather than escaping. And in this way, they zigzag down the length of the fiber at nearly the speed of light. The information they carry is encoded in the pattern of their pulses, photons on, photons off, like a very fast Morse code written in light. A single fiber optic cable can carry enormous amounts of data because photons can be pulsed billions of times per second, and because multiple wavelengths of light can be sent through the same fiber simultaneously, each one carrying its own independent stream of data. This technology is what makes the modern internet possible. The vast majority of long-distance data traffic in the world travels as photons through glass fibers laid along ocean floors and buried beneath city streets. Every message you send, every image you receive, every voice you hear through a video call has likely traveled as light through glass at some point along its journey. Medical X-rays use high-energy photons to create images of the inside of the human body. X-ray photons have wavelengths much shorter than visible light, which gives them enough energy to pass through soft tissue, skin, muscle, organs, while being absorbed or scattered by denser materials like bone and metal. When a beam of X-ray photons is directed at the body, those that pass through create an image on a detector behind the patient. The areas where photons were blocked appear white or light grey on the image, revealing the shapes of bones and dense structures, while the areas where photons passed through appear dark. This simple principle, that different materials absorb photons differently, has saved countless lives by allowing doctors to see fractures, tumours, infections and foreign objects without surgery. An X-ray image is in essence a shadow made of light. Not visible light, but light of a much shorter wavelength and higher energy, light that can penetrate flesh and reveal what lies beneath. It is one of the most elegant medical applications of the photon, a use of light to see what the eye alone could never see. Microwave ovens heat food by using photons in the microwave frequency range. These photons have wavelengths measured in centimeters, much longer than visible light, and they carry a specific amount of energy that is well matched to causing water molecules to rotate and vibrate. When microwave photons enter your food, they are absorbed by the water molecules inside it, and the energy of each photon is converted into molecular motion, the rapid spinning and jostling of water molecules against their neighbors. This molecular motion is what we experience as heat. The food warms from the inside out, not because the microwaves are hot in themselves, but because they are tuned to a frequency that water absorbs efficiently, and the absorbed energy becomes thermal energy. It is a remarkably targeted form of heating. The photons do their work primarily on the water content of the food, which is why dry materials heat more slowly in a microwave. Every time you warm a cup of tea or heat a plate of leftovers, you are filling the chamber with trillions of microwave photons, each one arriving at a water molecule and giving it a tiny push, a tiny spin, a tiny contribution to the warmth that you will soon hold in your hands. The remote control for your television most likely communicates using infrared photons. When you press a button, the remote emits a rapid sequence of infrared light pulses from a small LED at its tip, pulses that are invisible to the human eye but perfectly detectable by a sensor on the television. The pattern of these pulses, their timing, their duration, the gaps between them, encodes a specific command: change the channel, raise the volume, turn the screen on or off. Each button corresponds to a different pattern, a different message written in infrared light. The photons travel in a straight line from the remote to the sensor, which is why you usually need to point the remote at the television for it to work. It is a quiet, everyday miracle of communication. Invisible light carrying instructions across a room at the speed of light, arriving at a sensor that reads the pattern and translates it into action. Every time you change the channel from the comfort of your couch, you are using photons as messengers, sending a beam of invisible light to carry your wishes across the room. Radio signals, Wi-Fi, Bluetooth and cellular networks all transmit information using photons at various radio and microwave frequencies. Every text message you send, every song you stream, every phone call you make, every web page your device loads over a wireless connection, all of these are carried by photons. The photons used in these technologies have very long wavelengths compared to visible light, stretching from centimeters to meters or even longer, and they carry very small amounts of energy per photon. But what they lack in individual energy, they make up for in abundance and in the sophistication of the encoding. The information is written into the pattern of the radio waves, their frequency, their amplitude, their phase, their timing, and your device decodes that pattern back into sound, text, or images. We live immersed in a constant invisible ocean of photons carrying data in every direction, signals passing through walls, through air, through your own body, unnoticed and unfelt. The wireless world we take for granted is a world of light, not the light you can see, but light nonetheless. Photons doing their ancient work of carrying energy and information from one place to another. Photons play a critical role in PET scans, positron emission tomography, one of the most sophisticated imaging techniques in modern medicine. In a PET scan, a patient is given a small amount of a radioactive substance that emits positrons as it decays. A positron is the antimatter counterpart of the electron, and when a positron encounters an electron inside the patient's body, the two annihilate each other. This annihilation converts all of their combined mass into energy, which is released as a pair of gamma-ray photons traveling in exactly opposite directions. Detectors arranged in a ring around the patient capture these paired photons, and by tracing their paths backward, a computer can determine exactly where the annihilation occurred, and therefore where the radioactive substance has accumulated. This allows doctors to see the metabolic activity inside the body in extraordinary detail, revealing tumors, brain activity, and the function of organs. It is a profound use of photons, light born from the collision of matter and antimatter, captured by human instruments and translated into images that can save lives. Ultraviolet photons from the sun are responsible for sunburns. UV photons have wavelengths shorter than visible violet light, typically between 10 and 400 nanometers, and they carry enough energy to damage the DNA inside skin cells. When these high-energy photons are absorbed by the molecules in your skin, they can break chemical bonds within the DNA, causing errors in the genetic code that the cell must then repair. When the damage is extensive, when too many UV photons have struck too many cells, the body responds with inflammation, increased blood flow, and the familiar redness and pain of a sunburn. This damage, accumulated over years, can lead to premature aging of the skin and increase the risk of skin cancer. Your skin produces melanin, a pigment that absorbs UV photons and converts their energy into harmless heat. And this is what causes tanning, the body's attempt to build a shield of pigment against further UV damage. Sunscreen works by absorbing or reflecting UV photons before they reach the skin's living cells. In either case, the story is the same. Photons from the sun, invisible to the eye but carrying enough energy to alter the chemistry of life, arriving at your skin billions at a time on every sunny day. A photon can be converted into a pair of particles, one particle of matter and one of antimatter, if the photon carries enough energy. This process is called pair production, and it is one of the most remarkable demonstrations of the relationship between energy and matter in all of physics. When a sufficiently high-energy photon passes close to an atomic nucleus, it can spontaneously vanish, and in its place, two new particles appear, most commonly an electron and its antimatter twin, the positron. The photon is gone, and in its place, matter exists where none existed before. The energy of the photon has been converted entirely into the mass and motion of the two new particles, in perfect accordance with the principle that energy and mass are interchangeable. The photon did not break apart, it transformed. It gave up its identity as light and became substance, traded its luminous nature for the weight and solidity of matter. Pair production is the universe demonstrating that light and matter are not as different as they seem, that under the right conditions one can become the other, and the boundary between energy and substance is not a wall but a door. The reverse of pair production is also true. When a particle of matter meets its antimatter counterpart, the two annihilate each other and produce photons. An electron meeting a positron, for example, results in the complete destruction of both particles and the creation of gamma-ray photons that carry away all the energy that was once locked in their mass. Nothing of the original particles remains. No fragments, no residue, no trace. They are gone, and in their place, there is only light. This is the purest conversion of matter into energy that the universe allows, a total transformation, a complete and perfect exchange. It is the inverse of pair production, the closing of a circle that began with light becoming matter and ends with matter becoming light again. Annihilation is not destruction in the way we usually think of the word. Nothing is lost. The energy that was in the particles is now in the photons, conserved perfectly, merely changed in form. The universe does not waste, it transforms, and the photon, that ageless and tireless messenger, is the form that energy takes when matter has finished being matter. Gravitational lensing occurs when the gravity of a massive object, a galaxy, a cluster of galaxies, or even a black hole, bends the path of photons passing near it, distorting or magnifying the image of objects behind it. This phenomenon was predicted by Einstein's general theory of relativity, which describes gravity not as a force pulling on objects, but as a curvature in the fabric of space and time caused by the presence of mass. When photons travel through space that has been curved by a massive object, they follow the curvature, bending their paths in the same way that a marble would curve if you rolled it across a stretched rubber sheet with a heavy ball sitting in the middle. The result, when seen from Earth, can be spectacular. Distant galaxies appear smeared into arcs, or duplicated into multiple images, or brightened into visibility by the natural magnification of the intervening mass. Gravitational lensing has become one of the most powerful tools in astronomy, allowing scientists to study objects too distant or too faint to be seen directly, and to map the distribution of invisible dark matter by observing how it bends the light passing through it. Einstein's general theory of relativity predicts that photons lose energy when climbing out of a gravitational field, a phenomenon known as gravitational redshift. When a photon is emitted near a massive object, such as a star or a planet, and travels outward into space, it must expend energy to escape the gravitational pull of that object. But a photon cannot slow down. It always moves at the speed of light. So instead of losing speed, it loses energy by shifting to a longer wavelength. Its color reddens, moving toward the red end of the spectrum, as though the gravity were gently stretching the photon's wave as it climbs away. This effect was confirmed experimentally in 1959 by Robert Pound and Glenn Rebka at Harvard University in an elegant experiment conducted inside a tower just over 20 meters tall. They measured the tiny shift in the frequency of gamma-ray photons as they traveled upward against Earth's gravitational field, and the result matched Einstein's prediction with remarkable precision. Gravitational redshift is the universe reminding us that gravity touches everything. Even light, even massless, weightless light must pay a toll to leave the embrace of a massive body. Cherenkov radiation produces a haunting blue glow when a charged particle travels through a medium faster than light travels through that same medium. This is not a violation of the cosmic speed limit. Nothing is moving faster than light in a vacuum. But as we have learned, the wavefront of light moves more slowly through materials like water or glass than it does through empty space, and it is entirely possible for a high-energy charged particle to outrun that slower wavefront. When this happens, the particle creates a shock wave of light, a cone of electromagnetic radiation that spreads outward from the particle's path, similar to the sonic boom created by an airplane exceeding the speed of sound. The photons produced by this shockwave appear as an eerie, glowing blue light, and this glow can be seen in the water surrounding nuclear reactors, where high-energy particles from the reactor are moving faster than the light traveling through the water. Cherenkov radiation is one of the most visually striking phenomena in all of physics. A blue glow born from speed, a luminous signature left behind by particles racing ahead of light through the depths of water. The Casimir effect demonstrates that even in what we call a vacuum, the emptiest possible space, something is happening. Quantum mechanics tells us that empty space is not truly empty. It seethes with temporary fluctuations, brief shimmers of energy that pop in and out of existence so quickly they cannot be directly observed. Among these fluctuations are virtual photons, photons that flicker into being for an instant and then vanish. In 1948, the Dutch physicist Hendrik Casimir predicted that if you placed two uncharged metal plates extremely close together in a vacuum, the space between them would restrict which virtual photons could exist there, while the space outside the plates would have no such restriction. This imbalance creates a measurable force that pushes the plates together, a force that has been confirmed by experiment. The Casimir effect is extraordinary because it reveals that the vacuum of space is not empty but alive with quantum activity, and that this activity has real physical consequences. Even nothingness, it turns out, has texture and energy. Even the void hums with the presence of light that is not quite there. Photons have a quantum property called spin, and the spin of a photon has a value of 1. Spin is one of the most fundamental properties of any particle, and it describes something about the particle's internal angular momentum, the way it rotates or twists in its own quantum way. But photon spin is not like the spinning of a top or a planet. It is a purely quantum mechanical property with no true classical equivalent, a number that determines how the photon interacts with other particles and with magnetic fields. A spin of 1 classifies the photon as a spin 1 boson, placing it in the family of particles that carry forces between other particles. The spin of the photon is what gives light its polarization. The orientation of its electromagnetic wave is intimately connected to its spin state, and the two cannot be separated. Understanding the spin of the photon is essential to understanding how light interacts with matter, how it is absorbed and emitted, and how it behaves in the strange and beautiful landscape of quantum mechanics. Spin is one of the quietest properties of the photon, hidden from everyday experience, and yet it shapes the behavior of light in every interaction. Despite having a spin of 1, a photon has only 2 possible spin states, not 3 as you might expect from a spin 1 particle. These 2 states correspond to right-handed and left-handed circular polarization, which describe the 2 directions in which the photon's electromagnetic field can rotate as it travels. A right-handed photon's field rotates clockwise when viewed from behind, and a left-handed photon's field rotates counterclockwise. The reason the photon has only 2 spin states instead of 3 is directly related to the fact that it has no mass. For massive spin 1 particles, 3 spin states are possible, 1 for each spatial direction. But a massless particle like the photon always travels at the speed of light, and this constrains its spin to lie only along or against its direction of motion, eliminating the third option. This subtle connection between mass and spin is one of the elegant symmetries of the quantum world. The photon's masslessness, which allows it to travel at the speed of light, also shapes its spin, which in turn shapes its polarization, which in turn shapes the way light interacts with everything it touches. Each property is woven into the others, a tapestry of constraint and consequence. In 2012, the Nobel Prize in Physics was awarded in part to Serge Haroche for his groundbreaking work in detecting and manipulating individual photons without destroying them. This was a remarkable achievement because, ordinarily, detecting a photon means absorbing it. The photon gives up its energy to the detector and ceases to exist. Haroche and his team developed a method using specially designed microwave cavities, tiny supercooled chambers with mirrors so perfect that a photon could bounce back and forth inside for a fraction of a second before being lost. By sending specially prepared atoms through these cavities, they could detect the presence of photons through the subtle effects the photons had on the atoms, without absorbing the photons themselves. It was the equivalent of reading a book without touching the pages, of observing without disturbing, of knowing without taking. Harosh's work opened new doors in quantum optics and quantum information, demonstrating that the quantum world could be observed with a gentleness that preserves what it measures. It was a triumph of patience, precision, and reverence for the smallest particle of light. Quantum cryptography uses individual photons to create communication channels that are, in principle, impossible to eavesdrop on without detection. The security of quantum cryptography rests on one of the deepest laws of quantum mechanics, that measuring a quantum system inevitably disturbs it. When two parties wish to exchange a secret key, they can send it as a series of individual photons, each one encoded with a specific polarization state. If anyone intercepts and measures those photons along the way, the act of measurement changes the photon's states in a way that the intended recipients can detect. The eavesdropper cannot copy the photons because quantum mechanics forbids the perfect cloning of an unknown quantum state. And the eavesdropper cannot measure the photons without leaving a trace because observation alters what is observed. This means that any attempt to listen in on a quantum encrypted communication reveals itself, and the two parties can discard the compromised data and try again. It is security built not on the difficulty of a mathematical problem, but on the fundamental laws of physics, a kind of encryption that does not rely on human cleverness alone, but on the nature of light itself. On Earth, the surface is bathed in an astonishing number of photons from the Sun. Approximately 1 quintillion photons, that is a 1 followed by 18 zeros, strike each square centimeter of the Earth's surface every second on a bright sunny day. This is the density of the Sun's generosity, the sheer volume of light that pours down from a star 93 million miles away and arrives at every small patch of ground, every leaf, every rooftop, every stretch of ocean. Each of those photons carries a tiny parcel of energy, and together they deliver the warmth and brightness that make life possible. They drive the weather, the seasons, the currents of the ocean. They feed the plants, which feed the animals, which feed the world. They warm the soil and evaporate the water and push the wind across the face of the earth, and they arrive in such staggering numbers that even the smallest area you can imagine, the tip of your finger, the back of your hand, is being struck by trillions of photons every second. You are standing in a rain of light so constant and so dense that you cannot feel the individual drops, only the warmth of the downpour. Every photon that has ever existed still carries with it the story of its origin. Its wavelength is a record of the event that brought it into being, the energy level an electron dropped between, the temperature of the surface that radiated it, the nuclear reaction that gave it life. A photon does not forget. It cannot forget. Its very identity, the length of its wave, the frequency of its oscillation, is a direct and permanent imprint of the moment it was born. When astronomers study the light from a distant star, they are reading that imprint. When a spectrograph separates starlight into its component wavelengths, it is unfolding the autobiography of photons that have been traveling for years, for centuries, for eons. The light falling on your closed eyelids right now carries within it the signature of the lamp that emitted it, or the screen that glowed, or the star that burned. Every photon is a messenger, and every messenger carries its letter faithfully, never altering a word, never losing a syllable, delivering its quiet truth across any distance the universe asks it to cross. This is the final and perhaps the most beautiful thing about a photon. It is light, and it is memory, and it is both of these things at once, forever. And so the photon goes on. Across the dark, across the distance, across the silence between the stars, it carries its small and faithful cargo of energy and truth. And you, lying here, resting, breathing, you are surrounded by these travelers even now. They are all around you, passing through the walls, drifting through the air, landing on your skin like the softest snow the universe knows how to make. You do not need to follow them. You do not need to understand them tonight. Just know that you are held in light, always, even in the dark. Let that be enough. Let that be the last thing you hear before sleep arrives. Good night.